So this is a simulation applet that I created in order to help students better visualize and understand the Hopfield model of auto-associative memory, which recently won the Nobel Prize in Physics. And to help students understand how this works, first of all, memories are stored in the brain through three stages. There's an encoding stage where neurons fire in response to a stimulus. So for example, maybe if I hear one particular song, there are 4 neurons in this 20 neuron brain that fire in response to hearing that song. Maybe song B has a second set of neurons that fire. Song C has another set of neurons that fire, etc. So each different song or pattern is associated with a different set of neurons that fire. This is how that particular stimulus is encoded in the brain. How does that encoding stabilize? How does it get stored as a long-term memory? Well, this is where the famous adage that neurons that fire together wire together comes in. So these 4 neurons fire together to encode the first pattern. And so according to what we would call the Hebbian learning rule, neurons that fire together wire together, they form excitatory connections amongst one another. Same idea for each of these other patterns. So each of these different set of 4 neurons that encode these different patterns form interconnected clusters of connections, right? So then the final stage of memory is retrieval. So let's say that I hear an incomplete part of that first song. So maybe it's a staticky version of that song. It's an imperfect stimulus of that first pattern. So maybe only the first 2 out of the 4 neurons fire in response to being exposed to that stimulus, right? Well, what the brain will do is, due to the connections between neurons 1, 2, 3, and 4, they will respond by spreading that neural activity from neurons 1 and 2 to neurons 3 and 4. Notice that in that first simulation I did, only neuron 3 activated. There's some randomness built into this model, which is actually more realistic, right? But in this particular example, neurons 1 and 2 started out by firing. It was an incomplete version of the first pattern. And that activity spread to 3 and 4 because in the storage phase of memory, these neural connections were forged based on the initial neural activity, right? So let me give another example here. Let's say that we have 2 patterns. And the first pattern is just neurons 1 through 10 activating. And the second pattern is, say, just all the odd neurons activating. So there's some overlap in the neural activity here. Maybe these are 2 songs by the same artist, so there's some overlap. They sound somewhat similar, right? When I learn that first pattern according to the Hebbian learning rule, I get connections amongst neurons 1 through 10. When I learn the second pattern, I get connections amongst all the odd neurons. And notice that some of these lines are thicker, indicating that, for example, neurons 3 and 7 were coactive both in the first pattern and in the second pattern. So that connection got extra strong. All right, so now let's say that I give a partial cue, an incomplete version of that first pattern. So it's almost the first pattern, except neurons 7 and 8 are not activated. What do you think is going to happen? If I compute the output, I complete the first pattern, but I also essentially complete the second pattern. This would be a failure to recall either of these individual memories, right? It doesn't match either one. So this neurons that fire together, wire together paradigm doesn't work, at least for this particular example. So John Hopfield, a physicist in the 80s, came up with an alternative learning rule. In this learning rule, you can have not only excitatory connections, but also inhibitory connections. And this learning rule says that if two neurons do the same thing within a pattern, if they either both fire or if they both remain silent, then the connection between them grows more excitatory. If they do opposite things, so in the second pattern, 6 and 7, one is not active, one is active, then the connection between them becomes more inhibitory. So if I learn that first pattern, I get connectivity like this. Notice that it's much denser, and there's excitatory and inhibitory connections. Then I learn the second pattern, and I get this final connectivity, right? So now if I start out with an incomplete version of, say, that first pattern, and I try to compute the output, now I do get a successful recall. This is called pattern separation between these two patterns, right? So that's just a short primer on how I used this simulation applet in order to help students actually visualize how neural activity is translated into neural connectivity for the storage phase of memory, and how that then aids in the retrieval of memories. So this is one of the leading theories for how memories are stored in the brain. And I use this in the classroom by first having students go through this visual aid, and then we leverage that to jump into the actual mathematical model of this. And by seeing this visual simulation first, they're able to understand the math much better.